Hello, this is Richard Cole. I'm going to be giving a series of videos on the pumping lemma for regular languages. I'm a faculty member at the Courant Institute at New York University. If you want to see more details, you can consult my webpage. Among other things, I have taught the undergraduate course on theory of computing at NYU multiple times. My research interest is in the area of the design and analysis of algorithms. And more particularly, for the last 12 plus years, I have worked in the area of algorithmic economics and game theory. And in particular, I am interested in algorithmic explanations for economic phenomena, such as why the invisible hand of the market manages to balance supply and demand. That is, manages to find prices that balance supply and demand. And fundamentally, this is a question about how efficiently one can transfer information within a market, within an economic market. Okay, at this point, you should have seen multiple examples of regular languages and how to demonstrate membership, how to demonstrate membership in such a language using DFAs and NFAs, and also how to represent such languages using regular expressions. However, many, and indeed most languages are not regular. And this sequence of videos is going to be about giving you a tool to demonstrate in a convincing way that particular languages are not regular. So let's just see a few examples of languages that are not regular. For instance, we might have L consists of strings which start with some number of A's and are followed with an equal number of B's. So this is a language and it's not regular. And intuitively, the reason is, if you wanted to recognize a string of this sort, once you'd finished reading the A's, you would have to know how many A's you had read. And in order to do that, it would seem, if you were using a DFA, that you would need a state for each possible number of A's. But since you could have any number of A's, this isn't a finite automata. Another non-regular language that we're going to be seeing is a language that consists of a repetition of a string. So W is just some string of A's and B's, and then our string is W followed by W. And again, to check that a string is in this form, it would seem you need to remember the first W in order to check that the second part of the string matches the first part. And once more, it doesn't seem that you can do this for every possible such string with a finite amount of memory, a finite amount of states. And for a very different language, very different looking language, this is a language over a single character alphabet, but a language which has relatively few strings. It's still an infinite number of strings. But here the strings consist of a sequence of A's where the number of A's in the sequence is a prime number. So 3 A's would be a string in the language, 17 A's would be a string in the language, but 16 A's would not be a string in a language. And again, this seems like something just too complicated to recognize with finite automata. At this point, probably don't see how to pull all of these things together, but what these videos are going to be about is providing you with the tool to be able to show that these languages and many other languages are not regular. In the previous video, I said we were going to learn how to show that many languages are not regular. So let's begin by looking at one of the languages we mentioned, which was the language of strings which have equal numbers of A's and B's, with the A's preceding the B's. And the way we're going to proceed is we're going to suppose for a contradiction that actually L is a regular language, which means that there's a DFA M that recognizes L. So let's suppose L were accepted by some DFA M. And given a machine, we can ask how many states it has. So let P be the number of states in machine N. And now let's consider a particular input. Let's look at the input, which we'll call S, which consists of PAs followed by PBs. And of course, this is in the language L. Now what we're going to do is we're going to look at the sequence of states that M goes through on reading this string. And so we begin at the start state, of course, let's call that Q0. And we read a sequence of A's, and let's just call the states we go through Q1, Q2, and so on and so forth. So eventually we've read the first PAs, and we've reached some state, call it QP. And now we keep going and we read the Bs. And eventually we read PBs, and let's call the state we've reached at that point Q2P. And the important point, of course, is as this string is in the language, we reach an accepting state. Now, this machine, by assumption, has only P states. That means there's got to be a lot of repetitions in this sequence of states. And in particular, there's a repetition in going from Q0 to Q1 to QP. This is a total of P plus 1 states that we've gone through, but there are only P different states, and therefore there must be a repetition by the time we've got to QP. Let me write that down as it's important. Must be a repetition at or before and let one such repetition occur. So let one repetition occur at Qi and Qj. What I mean by this is that Qi and Qj are actually the same state, but we have J comes later than I in this sequence, and furthermore, P is greater than or equal to J. So Qi occurs somewhere here, Qj occurs somewhere here. Now I'm going to redraw this picture to emphasize the pieces that we have. So we start at Q0. At some point we get to Qi, which is where we have the repetition, and we end, of course, at Q2P. And Qi is the same state as Qj. So now looking at the sequence of states we go through and viewing this as a graph, we are going to read some I repetitions of A in going from Q0 to Qi. Then we're going to read a further J minus I A's in going from Qi to Qj, so that by the time we've reached Qj, we've read a total of j a's, and then we read the rest of the string in going to the recognizing to the final vertex Q2p. So this is another p minus j a's followed by p b's. And let me just give some names to these pieces of the string. I'll call the initial I a's x. I will call the following j minus I a's y, and I will call the remainder of the string z. So my string a to the p, b to the p can also be written as a concatenation of x, y, z. And x, y, z is an L. Now, this picture, this graph, shows a set of paths that exist in our finite automata. So let me ask, what happens if I read the input string x, y, y, z? Well, if I read x, this is the DFA, it's going to take me from Q0 to Qi. Then in reading y, I go from Qi round this loop back to Qj. If I read y a second time, I go round this loop a second time. And then when I read z, that takes me from Qi or Qj, it's the same state after all, to this accepting state Q2p. And that means that x, y, y, z is also in my language L. But what is x, y, y, z? X, y, y, z is a to the I, a to the j minus I, a to the j minus I again, and then a to the p minus j, that is p minus ja's, followed by p b's. Let's just add up the number of a's that we have. And what you see is we have p plus j minus I a's. And the important point to remember from a minute ago is that j is greater than I. So the number of a's and the number of b's in x, y, y, z are not equal. There are more a's than b's. But that means that in fact, x, y, y, z is not in the language L, because the language L consists of those strings with equal numbers of a's and b's, with the b's following the a's. So we've managed to deduce that this string is in the language L and also that it isn't in the language L. That's a contradiction. And what was our assumption? If we look back at the previous slide, what we see is we assumed that L was accepted by some DFA M. And so that assumption must be incorrect. So we can conclude, our conclusion is that L is not accepted by any DFA. In other words, L is not regular. Okay, so let me summarize what was going on. The key to our argument was to show that we had a string and the path that it caused us to follow in the DFA has a loop in it. And if we label these three pieces of the path by the strings that cause us to traverse them, namely x, y, and z, then what we know is that both x, y, z and x, y, y, z are accepted. And That's what is going to give us a contradiction. And one way to look at this is a DFA is really a directed graph. And in order to accept a string, you follow a path from the start vertex to an accepting vertex or accepting or final vertex. And if the string is long, the path that you're following has to be equally long. And in a finite graph, eventually you're going to get to strings whose lengths force the corresponding path to have a cycle. And once you've got a cycle, you can get a repetition of the form that we've just shown here. And that then allows you, in cases that the language is not regular, to pull out a contradiction. In the previous video, we showed the following language was not regular. L consisting of strings with some number of A's followed by an equal number of B's. Now, we could give similar arguments to show indeed all of the other languages I mentioned to you at the start that are not regular using this method. But it would be a bit annoying and to have to go through this style of proof and to craft it language by language. So what I'm going to give you now is a result called the pumping lemma, which captures the essence of these arguments, and in particular the notion that if you've got a regular language and long strings in the language, then you're going to have a cycle in the path that the string follows when being read by the DFA. So let me now state the pumping lemma. And the reason for its name will become clear in a minute. So the pumping lemma actually applies to regular languages. So let L be a regular language. And what it does is it gives a property of regular languages. And it's a property that non-regular languages are, for the most part, going to fail. And for that reason, we're going to be able to show that they're not regular. So what the result says is that there is a constant P, and I'll write it P sub L to emphasize that it depends on the language in question, called the pumping constant for L. So it's one constant per regular language, such that for every string S in the language that's long enough with S of length at least P, S can be pumped. And I'll explain what pumped means momentarily. That is, we can write S as the concatenation of three strings, X, Y, Z, and X, Y, and Z satisfy certain properties. First of all, the length of X and Y is reasonably short. It's at most P characters. Second, the length of Y is at least 1. That is, Y is not the empty string. X could be the empty string. And third, and this is really the crucial property, let me call the following string S superscript I, which is X followed by Y repeated I times, followed by Z. This is in our language for all integers I. So what this means is that XZ, XYZ, XYYZ, XYYYZ, and so on are all in the language L. And of course, XYZ is the original string S, so of course it's in L. All right, what I'm going to do now is show you a proof, and then I will show how to use the pumping lemma to show that languages like this particular L are not regular. So, as L is regular, there must be a DFA that accepts L. So let M be a DFA accepting L. And suppose M has P states. Since M is a DFA, it has some number of states, and just call that number P. And now I'm going to consider a particular string S. And it's going to be a string in my language such that S has at least P characters in it. And let me write S as just a sequence of characters. Let's call them A1, A2, AR. Well, of course, R is at least P. And each of these A's is a character in my alphabet. And let's look at the computation of M on input S. So the computation of M on input S. It goes through a sequence of states. It begins at the start state, call it Q0. And it reads the first character in the string, A1, which brings it to state Q1, say. Reads the second character, which brings it to state Q2. And we keep going in this fashion. When we've read the pth character, we will reach state QP. And we keep reading. And when we've read the rth character, we will reach an accepting state, call it Q sub R. Now, this is not to say all these states are distinct. It's just the sequence of states that M goes through on reading this particular string. Now, what we know is by the time we've got to QP, we've gone through P plus 1 states. So as before, there must be a repetition. So we must repeat a state by QP. And let QI and QJ be a repeated pair. With I strictly less than J, less than or equal to P. There has to be such a pair. All right, let me, as before, redraw this picture. To focus on the pieces of this path. So we start at Q0. We have Qi equals Qj. There's an initial portion of the string that we read, namely namely A1, A2 through AI, and let me call that X. Then the next portion takes us from Qi to Qj, meaning back to Qi, and that's AI plus 1 through AJ, and let me call that Y. And then the final portion of the computation brings me to QR, and that happens on reading AJ plus 1 all the way up to AR, and let me call that portion Z. So I'm just renaming the pieces of the string that I read. So indeed, the string I chose can be written as X, Y, Z, because it's just A1 up to AI, followed by AI plus 1 up to AJ, followed by AJ plus 1 through AR. And of course, this is in the language L because we assumed S was in L. But now let's look at SI equals X followed by Y repeated I times followed by Z. What happens when we read this string? Well, X takes us from Q0 to Qi. Each repetition of Y takes us around this loop, that is from Qi back to Qi or to Qj, which is the same thing. And once we've done I repetitions of the Y, what do? We read Z, and Z takes us from Qi, which is Qj, to QR, which means that the string SI takes us from the start state to an accepting state, and therefore it too is in the language, which was the third of our claims. Now let's look at the other two claims. We said we wanted that XY has length at most P. But that's true because reading X then Y gets us to QJ. And going back to the previous slide, what we see is that we assumed j was less than or equal to p. Not we assumed, we know that j is less than or equal to p. So that means by the time we've reached j, we've read j characters. Sorry, by the time we reach qj, we've read j characters, which is at most p characters. So xy is less than or equal to p, and y has length greater than or equal to 1. Why is that? Well, again, let's go back to the previous slide. We have that I is less than j. And so in going from qi to qj, we read one or more characters. And those are the characters that make up y, and therefore y has length at least 1. So now, going back one more slide to see the statement of the lemma, we have shown these three properties. Length of xy is at most p, length of y is at least 1, and all the strings x followed by I repetitions of y followed by z are in the language L for any integer I. I is 0, I is 100, I is 1,000,000, it doesn't matter, they're all in the language. And that's the proof of the pumping lemma. Now, how do we use the pumping lemma? Supposing I want to show L equals a to the I, b to the I greater than or equal to 0 is not regular. How do I do it? So our first step is to assume for a contradiction that L is regular. Then we can apply the pumping lemma to L. So that means that by the pumping lemma, there is a constant P or P sub L such that for every S in L with S of length at least P, S can be pumped. And the pumping lemma specifies what being pumped means. So that was step 1. Step 2 is to choose an S. And the S I'm going to choose is the one we saw before, namely the string of PAs followed by PBs. Now notice that S is in the language L and S has length greater than or equal to P. Therefore, S is a string that can be pumped. So we can pump S. That means that we can write S as X, the concatenation of X, Y, and Z with XY having length less than P, Y having length greater than or equal to 1, and for all I greater than or equal to 0, X followed by I repetitions of Y followed by Z is in the language L. So let's look at our original string, S or S1. So here's a drawing of it. It comprises PAs followed by PBs. And we can break it up into these three pieces, X, Y, and Z. And what we know is that Y has length at least 1, it's a non-empty string, and X and Y have total length at most P, which means they have to sit in this initial block of PAs. So now let me look at S0. So that's the string made up of xa's, let me say a to the x, so that's x followed by z. And this would be a to the p minus the length of x minus the length of y followed by p b's. Now, by the pumping lemma, this string is in the language L. But let's look at this string. How many a's does it have? Well, we got length of x a's here, and p minus length of x minus length of y a's here. So in total, S0 can be written as a followed by p minus length of y a's followed by p b's. And remember that y is at least, the length of y is at least 1. That means this string has fewer a's than b's, which means it's not in the language L. This is a contradiction. And as we have a contradiction, it means that our original assumption must be wrong. And what was the assumption? Let's look back at step 1. It was the assumption that L is regular. So in fact, L is not regular. And this is how one uses the pumping lemma to show that languages are not regular. Step 1 is just setting up everything. You assume that the language is regular for a contradiction, and note that you can apply the pumping lemma to long enough strings in the language. Step 2 is to choose an S, which is in the language and which is long enough. And then I should really call this part step 3. It's the consideration of a pumped string, in this case S0, and deducing that it's both in the language, which follows by the pumping lemma, and that it's not in the language, which comes from looking at the particular structure of the string in this particular language and seeing that somehow it doesn't obey the properties that the strings in the language have. By the way, we call this process pumping up. And I'm sorry, this is pumping down. And shortly, we will see an analogous process which is pumping up. Actually, I want a new page for that. So in doing the proof, I could instead look at the string S2, which is obtained, so this is X followed by Y again, followed by Z. So X, Y, Y, Z. And what is this? This is length of X A's, length of Y A's, length of Y A's, and as before, P minus length of X minus length of Y A's and P B's. So this too is in the language by the pumping lemma. And how many A's and B's does it have? Well, if we add this up carefully, we'll see that S2 consists of P plus length of Y A's followed by P B's. And again, as the length of Y is at least 1, this string does not have equal numbers of A's and B's, and therefore it is not in the language. So this is an alternative proof of the result, and we call this variant of it pumping up. So it's pumping up is when you introduce more copies of Y, pumping down is when you remove all the copies of Y. So let me finish up by making a few observations about applying the pumping lemma. First one is this argument must work for all values of P. When you've assumed that the language L can be recognized by a DFA, you don't, actually know which DFA recognizes it. So you don't know how many states that DFA has. It just has some number of states that you call P. And really what you're doing is you're showing that whatever DFA you consider, it doesn't recognize the language. And so you've got to be making an argument that works for all values of P. The second thing is your argument must work for all choices of X and Y with XY having length at most P and Y having length at least 1. You don't get to choose X or Y. And this, by the way, is a very common mistake when doing these proofs, when making these arguments. Your argument has to work for every possible X and Y, modulo that they're not too large. That is, together the length of X and Y is at most P, and the length of Y is at least 1. But you do have one thing to choose. You get to choose S. Now let me note that S will depend on P, but otherwise is fully specified. So for our example language L, we had L was PAs followed by PBs. So since we didn't know P, we had to leave that as a variable. And it can appear as a variable in our string, telling us how many times to repeat a character or a pair of characters or whatever it is you want to repeat. But everything else must be specified. The characters that you're repeating have to be named. Okay, let me leave you with a question to consider. The argument I gave, the proof of the pumping lemma, I gave for DFAs. My question is, does the proof work for NFAs? So can you take the argument, maybe making small modifications and have a result that applies to an NFA? So instead of assuming that L is recognized by a DFA, just assume that L is recognized by an NFA, and the NFA has P states, and then is the argument basically correct? Or if it isn't correct, point out where the argument breaks down. Okay, that concludes video 2. In the last video, we proved the pumping lemma and used it to show that one language was non-regular. In this final video, we're going to show several more examples of non-regular languages and give proofs that they are indeed non-regular. So let's get going. Let's look at the following language. L2 is the strings W such that W has equal numbers of A characters and B characters, but in no particular order. Well, we're going to begin by using the same proof as for the language that we saw before, namely let's call it L1, which had equal numbers of A's and B's, but with the A's coming before the B's. So we do this by considering the string S is A to the P, B to the P. And pumping, as we saw in the previous, in the proof for the language L1, produces a string with unequal numbers of A's and B's, and hence a string that's not in the language L2. So that would be one way we could prove it, but I want to give you an alternate proof. And to see this, to follow this alternate proof, you need to remember that the intersection of two regular languages is also regular. Now, maybe you don't recognize this immediately, but you know that the union of two regular languages is regular, and you know that the complement of a regular language is regular. And the thing is, intersection can be expressed as a combination of union and complementation. So in fact, the intersection of two regular languages is also regular. And just to see this, let me remind you that A intersect B is the complement of A union the complement of B, all complemented. So it's just the intersection of two regular languages A and B is a combination of complements and unions of regular languages. Now, let's look at L2 intersect A star, B star. What does A star, B star mean? This is the language of strings that consist of a number of A's followed by a number of B's. And maybe it's 0 A's, maybe it's more than 0 A's, and likewise for the B's. And what is this language? Well, L2 says we've got equal numbers of A's and B's, and A star, B star says the A's come before the B's. So it's exactly the following. Equal numbers of A's and B's with the A's before the B's. So once we've taken this intersection, we get L1. Then if L2 were regular, then so would then L1 would also be regular. But we know L1 is not regular, we just proved that. And so L2 cannot be regular either. And in fact, you should see that this is a proof by contradiction. If I said it slightly differently and more formally, I would start by saying, suppose for a contradiction that L2 were regular. Then intersect it with the regular language A star, B star, which gives me a new regular language, and that new regular language happens to be L1. And so I've just shown that L1 is regular. But I know L1 is not regular, and so I have a contradiction, and so my assumption is wrong. But that level of formality gets a little tedious when something is this straightforward. And so I didn't do it. Okay. Okay, my next example, call it L3. The strings of the form W, W reversed, where W is a string of A's and B's. So, e.g., ABA, ABA, or ABB, BBA, right? The first three characters is W, the second three characters is the reversal of W. W with the superscript R just means the string in reverse order. So how do we prove this? Well, we begin by assuming for a contradiction that L3 is regular, and then we note that we can apply the pumping lemma to L3. And so let's look at a particular string S, and this is going to be the string I choose. PAs followed by 1B, this will be my W, and then I'll reverse it. So it's P followed by, it's B followed by P more A's. So let's just note S is in my language L3, and S has length greater than or equal to P. So I can pump S. Now let's draw out what S looks like. So we've got PAs, we've got a B, we got a second B, and we got another PAs. And when I apply the pumping lemma to this, let's remember what that means is I can write S as the string X, followed by the string Y, followed by the string Z. And the important things are that X, Y together are at most P characters long, which means they lie in the first PAs, and Y has length at least 1. So now let me look at the string S0, which I get by removing the Y. Whoops, I'm doing a removal, better be a bit shorter. I have X followed by Z. So what is this? It's going to be length of XAs, then length P minus the length of X minus the length of YAs, BB followed by PAs. Okay, and by the pumping lemma, this is in my language L3. Question is it actually in L3? So this string, let me rewrite it. What is it? S0 is A, how many A's do we have at the beginning? We have P minus YAs, then we have 2 B's, and then we have PAs. And my question is it in L3? So is it equal to V followed by V reversed for some V? Well, if it were equal to V followed by V reversed, as I've got just 2 B's in this string, I would need this piece to be V and this piece to be V reversed. But I see that's not the case because I've got PAs in the V reversed, and I've only got P minus YAs in V, and Y is the length greater than or equal to 1, and therefore I have fewer A's in my candidate V than I have in my candidate V reversed. So in fact, that's not possible. And so S0 is not equal to VV reversed for any possible V. So S0 is actually not in L3. And I've got a contradiction because I've shown S0 is in L3 and S0 is not in L3. And therefore the assumption that I started with, which I didn't write down, namely that L3 was regular, is not a correct assumption. Let me say, when you're writing out an argument that a language is not regular using the pumping lemma, you should write it out properly. That is, you should write down, suppose that L3 is regular. Then the pumping lemma can be applied to L3. I'm, for lack of space on this slide, and in order to get through the lecture in a reasonable time, I'm not writing out all these details. One thing is, when making this argument that the string S0 is not in L3, has to hold for any partition of this string into an initial string V and a final string, which you need to argue is not V reversed. So you need to make some argument that this is not of the form V reversed. It is not just that this is not the string W reversed that you started with. It's that it can't be rewritten as V reversed for any V. Okay, and let me mention one common mistake. So this is to encourage you not to make this mistake. It's a common mistake is to do something like this. Define S is equal to W reversed repeated P times. The trouble is, this isn't the definition of a string because W hasn't been defined. And it's pretty much impossible to make an argument starting from this because you don't know what W is. My next example is L4. This is quite different sort of example. It's a single letter alphabet now. All the strings are strings of A's. And this is just telling you how many A's there are. I is an integer, so you could have I is 0, and then this would be the empty string. I is 1, it would be a single A. I is 2, so I squared would be 4. That would be 4 A's. I is 3, it would be 9 A's, and so on and so forth. And intuitively, it does seem that this can't be regular. How would you test that you've got a quadratic number of A's in your string? And so let's try and use the pumping lemma to prove it. Again, we suppose that L4 is regular for a contradiction. And then for long enough strings, we know that are in the language, we know that they can be pumped. So let me look at the following string. S is a to the p squared, where p is the pumping constant for this language. And let me just observe the next shortest string in L4 is a to the p plus 1 squared. So it's p plus 1 squared number of A's, which we can calculate as p plus 1 squared is p squared plus 2p plus 1. So let me just draw a picture here. A p squared. This is my string S. Let this be a to the 2p plus 1. So this longer thing would be my string S primed. But now let me think about pumping S. So what happens, here is S. We have 3 bits, X, Y, Z. And what we know is this is of length at most P, and Y is of length at least 1. And so let's look at S2. This is X, Y, Y, Z. And how long is this? Well, S is a to the p squared in length. This is a to the p squared plus length of Y. And I observe that p squared plus length of Y is strictly greater than p squared because Y has at least length at least 1. And it's at most p squared plus p because xy has length at most p and therefore y has length at most p. And this is less than p squared plus 2p plus 1. So the thing is, this string is shorter than the next shortest string in L4. And so in fact, it can't be in L4 because it's longer than the string we started with, but it's shorter than the next shortest string in L4. And what I call this technique is pumping into the gap. And this is a technique that will work whenever your language is sparse. That is, it has few strings in it, and the gaps between successive strings in terms of their lengths are getting longer and longer. And then there's not going to be a finite automata that recognizes your language.